In the previous lecture, we talked about doing inference about a single proportion in a single population. In this lecture, we're going to expand that framework and talk about finding differences between two proportions. So these methods are useful when we're interested in comparing two populations to one another. So for example, let's say that we have a research question that asks whether Americans under the age of 35 are more likely to identify themselves as members of the Democratic Party than Americans over the age of 35 are. So is there a difference in these proportions of support for the Democratic Party depending on age? So we have two different populations that we're looking at, Americans under the age of 35 and Americans over the age of 35, and we want to compare this particular proportion across those populations. So in this lecture, we're going to talk about the methods that we need to answer that question. So let's kick off by considering a question for our example in this lecture. So scientists predict that global warming may have big effects on polar regions in the next century. So one of the possible effects is that the northern ice cap might completely melt. So the survey question asks, would this bother you a great deal, some, a little, or not at all, if the northern ice cap actually did completely melt? In this lecture, we're going to be looking at two different sets of responses to this survey question. So the question was asked on the General Social Survey in 2010. So we have data from the General Social Survey, which is a random sample from the US adult population. The question was also given in a survey to students at Duke University in an introductory statistics class. So we're going to be comparing the responses to this question in the general United States population and among these students at Duke University. So there are a couple of different ways that a respondent can answer this question. They can say that they'd be a great deal concerned, some concerned, a little concerned, or not at all concerned about the ice cap. We are going to focus on just one of those categories of responses, which is people saying that they would be concerned a great deal by the northern ice cap completely melting. So the question that we're interested in is whether the proportion of people who would be bothered a great deal by the ice cap melting is different in the general population and the population of Duke students. The parameter of interest we're working with is one proportion minus the other, and we're going to estimate the population parameter using a point estimate from the sample, so the sample proportions. In this case, the proportion of Duke students in the sample answering this way minus the proportion in the GSS sample answering this way. The basic elements of our approach to answering this question are going to stay the same as they have throughout the whole class so far. We are going to calculate a confidence interval around our point estimate with a margin of error that's equal to a critical value times a standard error. Our hypothesis test is just going to be a z-test where we take our estimate from the sample minus the null value divided by our standard error. So the only additional piece of information that we need is what the right standard error is for this difference between two proportions. So the standard error for the proportion of Duke students minus the proportion in the US population. So this standard error formula is printed here. It is the estimate in one of the populations times 1 minus that estimate over the sample size in that population, plus the same thing for the second population that we're studying. So we'll work through this in a little bit, but this is the standard error for the difference between two sample proportions. So as always, there are some conditions for inference that we need to take into account before we go ahead with our testing approach. The first of these conditions is really similar to the independence conditions that we've been talking about up to this point. So independence within groups just means that in both samples, the observations in the sample are independent of one another. We can help verify this by making sure that both samples are taken randomly and that each of the sample sizes is less than 10% of the population that they're drawn from. So for this particular example, we can assume that the attitudes of Duke students in the sample are independent of one another and attitudes of the US respondents are independent of one another. The second thing that we need to check is independence between groups. So not only do the observations within each sample need to be independent of one another, but the observations across the samples need to be independent of one another too. So the answers of the Duke students in that population or in that sample need to be independent of the responses of the United States residents in the other sample. And then the third condition is something that we talked about in the previous lecture, which is success and failure. So again, our condition is just that there are at least 10 observed successes and 10 observed failures in the two groups. That just means that across these categories that we're comparing, we have at least 10 observations in each of them. So we're going to continue with our example by constructing a 95% confidence interval around this point estimate of the difference between the proportions of Duke students and all Americans who would be bothered a great deal by the melting of the northern ice cap. So the first thing that we need to do is separate out our response categories into just two options: the people who responded that they would be bothered a great deal, and then a pooled category of all of the other responses. So you can see that in this data table here, as well as the totals in each of those samples, as well as the p-hat estimate, so the estimate for the sample proportions for each of those samples in the bottom row there. So the formula that we're going to follow is our point estimate, so p-hat for the Duke students and p-hat for the US population, plus or minus our critical value times the standard error. And this is just the standard error formula that we talked about on the previous slide. So let's go ahead and work this out. So we are just going to fill in the variables in this formula with the data that we have in this table above. So first, we're going to construct our point estimate by taking p-hat for the Duke sample minus p-hat for the US sample. So that's 0.657 minus 0.668, plus or minus the critical value for the 95% confidence interval. Remember, we're using critical values from the z-table because the sampling distribution of sample proportions is approximately normal under the conditions that we have here. So we can use the normal approximation and therefore use the critical values from the normal probability table. So 1.96 times the standard error. The standard error is constructed with the data for each of the samples. So we have 0.657, which is p-hat for the Duke students, times 0.343, which is 1 minus p-hat for the Duke sample, divided by the size of the Duke sample. And then we add that to the equivalent variables in the US sample. So p-hat, 1 minus p-hat, and then n for the US sample. And then when we work this all out, we're going to get the point estimate of negative 0.011 plus or minus 0.097, which gives us a 95% confidence interval from negative 0.108 to positive 0.086. So aside from constructing confidence intervals, the other main thing we need to know how to do is a hypothesis test. And the first step for doing a hypothesis test is to specify our hypotheses. So, which of the following is the correct set of hypotheses for testing this research question that we have about the difference in proportions of Duke students and the general American population who would be bothered a great deal by the northern ice cap melting? Take a look at these options and see what you think. So there are actually two of these sets of hypotheses that are both fine. They're actually mathematically equivalent to one another. So in hypothesis set A, the null hypothesis says that the proportion for the Duke students is equal to the proportion for the general US population. In the hypothesis set C, the null hypothesis says the proportion for Duke students minus the proportion in the United States is equal to 0. And those are, of course, the same expression as one another. And then the alternative hypotheses in each of those just have those two proportions not equal to one another or not equal to 0 in hypothesis set C. So both of those sets of hypotheses would be perfectly fine. The options that are wrong have p-hat as part of the hypotheses. Now remember, p-hat is a sample statistic, and our hypotheses are always about population parameters. So both of those sets of hypotheses are wrong. So just a quick recap from last lecture. Remember, we talked about there being a difference in the variables that we need to use for confidence intervals and for hypothesis tests. When we are working with confidence intervals, we want to be drawing all of the numbers that we need to construct that confidence interval from what we observed in our sample. Whereas when we do a hypothesis test, we want to make sure that we are setting up a distribution under the null hypothesis to compare what we observed to. So the numbers that we're going to use for constructing standard errors and stuff are different depending on what we're trying to do. So when we worked with one proportion, we wanted to make sure that the observed number of successes and failures were at least 10. And when we did a hypothesis test, we wanted to make sure that the expected number of successes and failures were at least 10. So now let's talk about how we are going to build on that to work with comparing two proportions. When we were doing a hypothesis test with a single population, we would have hypotheses like the proportion in the population in this particular category is equal to 0.8. So we would have this value p, 0.8, that we could use to calculate our expected numbers of successes and failures when we did our hypothesis test. Now, when we're looking at two proportions, the form of our hypotheses is different. We are looking instead at the hypothesis that one proportion is equal to another proportion. So that hypothesis is not set up to give us a null value for that parameter p. So instead, what we're going to do is we're going to create what's called a pooled estimate of a proportion. And we're going to use this formula that this pooled estimate is equal to the number of successes in the first sample plus the number of successes in the second sample divided by both sample sizes added together. And this is going to give us a null value for this parameter p. So let's calculate this null value for the example that we've been talking about. So this is the estimated pooled proportion in both the Duke sample and the US sample, who will be bothered a great deal by the melting of the northern ice cap. So we're going to take the number of successes in the US sample plus the number of successes in the Duke sample divided by the size of the US sample plus the size of the Duke sample. That's going to add up to 523 divided by 785, which equals 0.67. So again, this is the null value for the parameter p that we're going to be using as we do our hypothesis test. This slide asks which sample proportion the pooled estimate is closer to and why. Think about that for a sec. So the estimate is closer to the proportion in the US sample, and the reason for this is simple. There's just more data in the US sample than in the Duke sample. So whenever there's more data in a particular sample, that sample is just going to have more weight. And so this pooled proportion estimate is going to get pulled toward that proportion in the bigger sample, and the Duke sample doesn't have that much weight. It doesn't pull the estimate down by much. So in the last part of this lecture, we're just going to bring all this together and actually do this hypothesis test to see if the proportion in the Duke sample is actually different from the proportion in the US sample. So our z-test formula is really familiar. It's going to be our point estimate from the sample. So that's the proportion for the Duke sample minus the proportion for the US sample. We're trying to see if those are different, minus the difference between those proportions under the null hypothesis. And of course, the null hypothesis sets those proportions equal to one another. It says that the difference between them is 0. So we're just going to take the observed difference in proportions minus the null hypothesis difference in proportions, so just minus 0 in the numerator here. And then of course we're going to divide this by the standard error that we've already talked about how to calculate. Remember, of course, that we're using the pooled proportion that we calculated on the last slide in place of the p variable in the standard error formula. So we're using a value under the null hypothesis to calculate the standard error. This is different from the approach we take when we're calculating a confidence interval, where in the confidence interval we take the p-hat estimate from the sample. Of course, in a hypothesis testing approach, we're going to take that p estimate from the pooled estimate that we just calculated. So that estimate was 0.6662. Here in the slide, I've just rounded that to 0.67. So in the standard error formula, you have 0.67 times 1 minus 0.67, or 0.33, divided by the sample size for each of the two samples. We add those two quantities together and take the square root. So this works out to be the difference in the proportions that we observe, so negative 0.011, divided by the standard error under the null hypothesis, which is 0.0495. So that gives us a z of negative 0.22. Now you should be able to just look at this z and tell that it's not likely to be significant. Remember, when we have big z-scores, those are associated with small p-values, which are what allow us to reject the null hypothesis. But of course, we can just go ahead and calculate out this p-value. We're going to take, this is a two-tailed hypothesis test, so 2 times the probability that z is more extreme than 0.22, or negative 0.22 in this distribution. So that ends up being 2 times 0.41, which is equal to 0.82. So that is a really big p-value, which means that we cannot reject the null hypothesis. So what that means is that when we compare Duke students to the United States population, it doesn't look like there's a difference in the proportion of those that would say that they are a great deal bothered by the melting of the northern ice cap. So these two different populations, when it comes to this particular question, are pretty similar to one another. We don't have any evidence to suggest that they are meaningfully different in terms of their answer to this question. And that is an overview of how we compare two different proportions from two different populations. Thank you for listening, and I'll see you next time.